Welcome to today's webinar, Dynamometer Engine Testing. My name is John Sonarakis, and I will act as the moderator for today's webinar. The presenters for today are Sujit Basu of HBM and Gregory Morus of D2T. Sujit is HBM's Test and Measurement Business Development Manager for North America. He has a PhD in physics, where his thesis was focused on materials characterization. He has over 20 years of experience in the data acquisition industry. Gregory has a master's degree from ESSEM, a university located in France, on automation and computer science applied to automotive. Gregory has been with D2T for 10 years doing engine and powertrain testing applications. He is now in charge of technical installations and project management in North America. Before we begin, I just have a few quick announcements in case you just logged in. I have everyone's lines muted, and they will stay muted throughout the webinar, but if you have any questions, please type them out in the Q&A box, and we will try to get them at the end, get to them at the end of the presentation. We do plan on recording this webinar, and we'll have the link to the presentation available to everyone soon after the webinar is over, and it will be posted on our website as well. So without further ado, I'll pass the controls over to Sujit, and we shall begin. Sujit?
Thank you, John, for the introduction, and welcome everybody for today's webinar on dynamometer engine testing. I am here with Greg Morus from D2T, co-presenting on this application, and as you'll see through our presentation how the offering from HBM in terms of sensors and data acquisition hardware and software from D2T, namely Morphee, makes dynamometer engine testing and meeting the challenges so much easier. So my overview includes a brief description of what a dyno testing involves, and some of you are already familiar with that technology, so I will not spend way too much time on it. We'll discuss what are the challenges of such testings, and these are feedbacks that we have acquired from over the years of working with various customers in the industry, both in automotive as well as agricultural industry. We'll then move into what type of sensors and how do you choose them, especially for your measurement relating to dyno. We'll then discuss the data acquisition hardware that's available, how the HBM's offering compares and helps you in getting your job done, and then we talk about as well as introduce D2T's Morphee software, and at the end we'll just do a simple demonstration of a dyno testing. So the automotive and agricultural testing disciplines has emerged over the years. In the good old days, a real vehicle test track was the way to do testing, even in the research and development phase, and they were known as road load data acquisition. They used real cars, predefined tracks, and had real environment as Mother Nature provided. As things progressed, this type of testing moved into the domain inside a laboratory, and they are nowadays more known as bench testing and evolving towards the future of testing, which is virtual testing, and we'll talk about that. But in bench testing, just like in real vehicle testing, like road load data acquisition, real components are used, active loads are used, but the environment is completely simulated and hence a virtual integration. And if we move even a step further away, in laboratory testing, almost everything is virtual except for the engine control unit, which is real. So even the vehicle becomes a virtual aspect of this entire testing. And all of these migration from the real vehicle test to bench test to lab test is done so that as research and development engineers, we have more control on various aspects and parameters of our test benches. So we can vary various things and not have Mother Nature in control of certain things, which do affect our measurements a lot. So as I was saying, in bench tests, the biggest advantage moving from a proving ground is a lower cost and, of course, a faster testing times than proving ground, because in proving grounds and actual road load data acquisition, not only the cost is higher, you need dummies and you have to dress up the car accordingly, and the situations has to be created to mimic real-world conditions. These bench tests are reproducible tests, even in demanding ranges, as compared to the other kind, where a lot of times, unless Mother Nature gave you the perfect ideal conditions, repeatable conditions, sometimes it is not possible to reproduce this test, and you may just get one shot at it. Whereas inside a laboratory, a lot of these controls are in your hands, and hence these tests are repeatable. There is less risk, no driver involved. Many tests can run in parallel. You can have multiple engines. If you have to do that, you have to have multiple test tracks in a real-world situation. And you can test the entire vehicle from parts to entire overall vehicle inside a test lab. These type of tests further are classified into three different types. They're functional tests, system tests, and durability tests, power load durability tests. In today's discussion, we are going to focus mostly on system tests. And system tests can be further classified as chassis, power unit, and drivetrain test. For today's discussion on dyno testing, we're going to focus on the actual powertrain test, drivetrain test, as well as the power unit test, both of which deploys Dynamometer entirely for this application. So for those of you who are not used to dynamometers and would like to know a little bit on what is a dyno is basically a tool for measuring torque output versus RPM of an engine for a specified application of the load. And there's various types of dynos that has evolved over the years in the industry. There's the inertial-based dyno, which involves a spinning mass or a large heavy drum. There's a water brake-based dyno, which is basically water pump-based. There's eddy current-based dyno, more or less the electromagnetic brake-based. And there's electric motor-based dyno, which is AC or DC type electric motor. The eddy current-based or the electric motor-based dynos are the most popular because they address over 80% of the application that customers are working on. And the eddy current-based dynos are very popular for high-power applications with low inertia and are very responsive. And on the contrary, the electric motor-based application are very flexible in terms of their control, have the ability to load the engine and the motor, and is useful for measuring the amount of friction when the engine is monitored. So essentially, there's two types of dyno available in the market that people talk about. They are the engine dyno and the chassis dyno. And the engine dyno, as you might imagine, is just testing the engine, whereas the chassis dyno is just normally testing the engine, but also the drivetrain along with it, which is more of a real-world scenario. So here's an example of a chassis dyno at D2T's test facility. You can see this is a sports car, and there are the drum rolls underneath the wheels of the car. That's a TestCell area, and inside there is a test monitoring area where engineers are sitting using computer controls, running the various aspects of the dyno. I can see some exhaust clamp on the lower bottom half of this facility as well, and some cooling liquids in the big drums in the far right-hand corner. Another example, which is just an engine dyno as opposed to a chassis dyno. Here is, again, another TestCell environment with the engine hooked up, and this is primarily what's used in R&D environment when people swap one engine with the next one or may have multiple bays running with parallel tests. But this is a popular engine test stand. So what are the test types that's performed in a dyno testing? There's a steady state type, there's a sweep type, and there's a transient type, and the new type of dyno testing people nowadays are also doing road load simulation. As expected in a steady state type dyno, the engine is held at a specified RPM and or torque by the dynamometer, whereas in a sweep type dyno, the engine is allowed to sweep. It could be inertia or a brake-based dyno. And in a transient type of application, the engine power and speeds are varied rapidly during test cycle. So aggressive throttle movements are available. The engine speed changes. But most of the time, this type of tests are used for vehicle emissions development and certification. In the road load simulation, a simulation of the road course or field is done using the engine. So there's a curve that the engine has to follow that simulates or mimics a real-world aggressive driving condition, and that literally indicates that there's torque gradients available. And AC dyno with low inertia applications are really popular for this type of test. So here's an example of the BMW powertrain test cell that is using the HBM data acquisition hardware, as well as D2T's AC dynamometer and data acquisition software. As you can see in the bottom left-hand corner, the dynamometer, the D2T AC dyno is showing up. A little bit of the engine is showing as well. And then this is the data acquisition portion that's inside the test cell, where all the data acquisition modules are mounted and cables are coming from the bottom connected. Here's the blow-up portion of it. And all of these are connected via an EtherCAT connection, which is a real-time bus, to the D2T automation software called Morphee. This is the same picture, but a little bit zoomed in without the engine in it. As you can see, this is the actual dynamometer, and all of the data acquisition hardware is right above it. A blow-up of that hardware connection, measuring temperature and measuring various other factors. Like, we're going to go through that in a few more slides coming up. These data acquisition hardware, since they're inside a test cell, are ruggedized. There's also a portion of the data acquisition hardware that's not inside the test cell, and it's inside a control room that need not be ruggedized. Both options are available for such applications. So what are the sensors that's used in a typical dyno testing? As you know, HBM is a premier vendor of various type of sensors, including torque and strain gauge and load cell, etc., etc. Torque is what's measured in a dyno application, and horsepower, or more popularly known as power, is actually calculated. So torque and RPMs are measured, and power is calculated using torque times RPM by 5252. And there's two types of horsepower. There's your brake horsepower, and there's your wheel horsepower that you can further subclassify these measurements into. In a brake horsepower, the HP measurement, the horsepower measurement with a dyno that can load the engine, whereas the wheel horsepower, the power is measured at the wheels on the chassis dyno. The other type of sensors that is very important and needs to be monitored in such measurements are, of course, temperature, which is vital to this power curve measurement. And this temperature may include the coolant temperature, intake air temperature, exhaust gas temperature. In addition, other measurements like pressure, the oil pressure, various actuators. If you care about measurements, fuel efficiency, you would be doing the fuel consumption measurement. Cylinder pressure for combustion analysis. Of course, the CAN bus, which is the universal bus inside a vehicle, that talks to hundreds and hundreds of sensors depending on the type of vehicle you're using, and has the ECU information. Also needs to be talked to from your data acquisition system. And other measurements like ambient condition temperatures, humidity, barometric pressure are also part of this test stand. The torque sensor is the most important for the dyno measurement, and HBM, of course, offers two classes of torque sensors. The T12 is the high accuracy torque sensors, and the T40 or T40 FM is the lower cost option. Both options are available, and it really depends on the application needs as to which torque sensor would be mounted for your engine or chassis dyno application. The data acquisition hardware that HBM offers in this realm is the QuantumX from HBM. QuantumX is a standalone data acquisition system that can also be distributed among several modules, can be rack mounted as well as PC tethered if you just need one module. So it is a versatile data acquisition system with its own signal conditioning built in. All you have to do is bring in your sensor and connect to it. As you learn going through the presentation, that QuantumX has many features that are very important and vital to dynamometer type of applications that is satisfied right out of the box. Being a distributed architecture, you can deploy many quantum modules and spread over the network using either Ethernet or a firewire cable. QuantumX is one of those versatile modules that can acquire up to 15 different sensors on any single input. The QuantumX 840A and the 440A qualifies for that type of measurement. So it is really popular in the R&D environment. Measurements like voltage, temperature, resistance, force pressure, displacement, torque, acceleration, CAN bus, they're all supported using one or the other kind of QuantumX modules. Not only can QuantumX do analog input measurement and CAN bus measurement, it has also the capability of doing analog output measure as well as digital input and digital output. And overall, the QuantumX data acquisition system also supports data recording and various bus communication capability, such as EtherCAD, which is a real-time bus, and onboard real-time calculations of various types of channels. And some of the common ones are, of course, peak measurement, and there are other measurements available depending on which module you choose and the application you're working on. In terms of local storage, it comes with a compact flash card, or it can be connected to your desktop PC or a server PC and be talked to as well remotely. In addition to having a local storage media, it also has a capability of using various other buses, such as RS-232, USB, GPS, to talk to a touchscreen or camera, or deploy other security aspects of it, as well as timing and triggering in terms of communications that's built in as well. But one of the biggest advantages of QuantumX is, of course, onboard math channel, which means as the data is coming in, you can make real-time computations of certain kind and class deterministically on that data that's coming in. And this involves, various type of peak measurements or addition or subtraction. And in some cases, using the QuantumX CX22 module, you can also do analysis of your stress versus strain, such as class counting, rosette calculation, time at level, and various virtual channels. So the QuantumX data acquisition hardware can be defined into 4 different classes. There is a universal input modules. This is low bandwidth. This is high bandwidth. And there is also the other modules, which is focused more on analog output, bus communications like EtherCAD and CAN bus. Previously, I was describing to you the 840 and 440A, and as I mentioned, this is one of the most popular modules available in the market for doing R&D work and fits in very well with Dyno application. Whereas other high channel count modules, and these are typically 4 and 8 channels, the high channel count modules can go to 16 modules, and you can daisy chain and connect modules together to get even more channels. The typical test cell environment is divided into 2 parts. There is a control room and there is a test cell. The test cell is where all the real action is going on. The system under test, be that an engine or a drivetrain, is connected to a load in the specific case of a dynamometer application. But this test cell could be an aerospace test cell, for example, instead of an automotive test cell, or an agricultural test cell, etc. But nonetheless, there is a data acquisition system sitting right inside the test cell, and traditionally this is a rugged version of the data acquisition system. This is the system that is subjected to a lot of noise and interference and variation in the ambient temperature and other environmental factors that it must sustain and still give you an accurate enough reading so that you have repeatable measurement. And there is other portion of the data acquisition system that resides in a control room, and this may not be a rugged system. This could be a non-rugged system just fine. You also have the actual computer, the control computer, which is running the data acquisition software, in this case D2T Morphee. And if your application requires some hardware in loop simulation, because in your dyno testing, you may have certain aspects of the application which is not developed yet, but there's a mathematical model that can work this aspect of the application. So using the software, you can run the simulation and in real time interact with the rest of the hardware, whether it's a system under test, the load, the data acquisition system, and do analysis, all using this EtherCAD bus. Inside the test cell, the various applications, depending on what you're working on, could include sensors like torque, force, vibration, temperature, crankshaft, camshaft speed, pressure of air and liquids, and various bus signals. On the data acquisition system that's in the control room, typically this carries analysis data to a data server, and it has various flexible analog outputs, CAN bus outputs that's available to the rest of the other application, and these does not or need not have to be into a real-time bus. So I've used two different colors here for the same reason. So this is an example of a dynamic crank angle measurement with QuantumX. The measurements were engine or cylinder position, pressure of the cylinder, various valve forces, strain and position, rotation, vibration, and of course torque. And in such measurement, a high-resolution encoder was used as well, so it can be characterized in a better accuracy. The QuantumX modules that were deployed were the MX460 and the 410, both of which is a highly dynamic bandwidth module, so they have wide dynamic range and wide dynamic bandwidth. This is because the sensors that are used, they are used to capture signals with lots of different frequency content in them. Here is an example of the 460 talking to the torque sensor, a high-resolution encoder, as well as an inductive sensor, which is AC-based. And here's an example of the 410 module that is talking to the various low-bandwidth sensors, such as strain, vibration, acceleration, force, etc., but with a high resolution on the encoder. So why is QuantumX ideally suited for dynamometer application? Dynamometer applications face various challenges, especially in the harsh environments they're working in. And for acquiring the data, as far as acquiring the data is concerned, there's various aspects of noise and interference issues that the end user has to deal with. And these type of noise and interference are traditionally classified under electromagnetic noise and interference. Electromagnetic noise are generated from your engine. For example, your fuel injectors every time they are firing, alternator, an engine control system, and even the AC power supplies that's powering the AC motor to drive the load. All of these aspects do come into picture and create a very inefficient EMI noise environment that has to be dealt with. And noise can be intermittent. It doesn't have to be periodic. You sometimes can predict it, and other times you cannot. But overall, it leads to a loss of your signal-to-noise ratio. And a loss of signal-to-noise ratio will reduce your dynamic range, and it will degrade your accuracy and hence the quality of the data you're getting. So QuantumX is one of the few hardwares available on the market that has built-in noise immunity. It uses galvanic isolation for common mode type of noises and carrier frequency excitation technology for electromagnetic interference type of noises. And dynamometer applications also requires distributed system. For example, one inside a test cell and one inside the control room. So these systems need to be synchronized. So time synchronization is also very important. Using firewire bus, QuantumX can synchronize data at less than 1 microsecond in the clock. And using the EtherCAT bus, it can transfer or drive data at 10 kilohertz or 10 kilohertz data every second. Interaction with the real-time modules may be required if you are doing some simulation using MATLAB, and that also requires a fast deterministic EtherCAT bus to drive all of this acquired data from your test cell into the modeling that you're running with. Dynamometer application requires a changing of variety of sensors, and this makes it time-consuming and calibration intensive. A lot of our end users have given us feedback that when they have to change a testing to another testing and the sensors do change from one class to another class, this requires them to redo the entire configuration, which is very time consuming. And as you will see in today's demonstration, how D2T's Morphee software and QuantumX from HBM helps you tackle the problem. There's two ways to do it. D2T offers a TED-capable software that runs on QuantumX, and QuantumX also supports TED sensors. And TED sensors can be a real-time saver for such application. However, if you do not have TED-based sensors, which means you have non-TED sensors, QuantumX also offers you another advantage. It gives you the capability of storing the calibration data on the DAQ device. So when you move around with the data acquisition module, your calibration information for the sensors moves with you. This makes it a lot less time consuming than the traditional way of configuring everything from scratch. Dyno applications also benefit from data repeatability. Comparing two dyno curves that are not compared using the same ambient parameters such as temperature is a big challenge in this industry because changing ambient conditions will impact the dyno measurements. QuantumX gives you repeatable results in a wide variety of conditions. For example, the QuantumX 840A module, as an example, will work up to 65 degrees Fahrenheit ambient conditions and still maintain accuracy. It enjoys the best-in-class accuracy for all the measurements we do, and QuantumX has the best-in-class accuracy between 0.01% to 0.05%, depending on the module we choose. Many of our customers have told us that the Dyno application today requires very small margin and measurement uncertainty because they are adhering to Six Sigma standards. So to deliver such low margin, all sensors, data acquisition, etc. must have at least 10 times better performance. What it means is that if you are required to deliver a 1% overall accuracy, you need 10 times better or 0.1% class sensors, data acquisition hardware, etc. that is working in real-world conditions, which means at conditions only at room temperature or temperatures where actual the dyno test is running at a higher temperature very likely. So temperature drift, common mode noise, interference, all of those are there to degrade your data, and QuantumX comes in to help combat that situation and still delivers you the accuracy that you seek and go after. Here's a view graph of how various noise and interference in your dyno applications affect your measurements. So the first one, as you see, is the red line is your actual signal. This is a strain signal over time. And when it sees some type of electromagnetic interference, look at the data, how noisy it is. Compare that to the signal. It is 20 to 40 times larger. So this data is unacceptable. And this interference may come in at any time unpredictably that you have not much control on in many cases. And look at the same data when acquired using the QuantumX hardware. You do not see any effect of the same noise and interference, the electromagnetic interference that was injected or imparted in front of the QuantumX system, because QuantumX system has carrier frequency excitation. So if you see such a noise, you can turn your DC excitation off and turn on your carrier frequency excitation, and the noise is not seen anymore. It goes away. In addition, QuantumX has built-in galvanic isolation, which means any noise that can creep in because of a difference in ground from the channel to the power source, or from channel to ground, or from channel to channel, because of galvanic isolation, QuantumX will prevent all of these noises to come into your signal. Thermal drift, QuantumX also has a very good amplifier design that makes it work up to 65 degrees Fahrenheit with less than 0.01% thermal drift. So this is an example of an amplifier that has not done so well in a thermal drift, and a QuantumX amplifier that works so well when injected even to thermal drift. I'll pass on my control to D2T now, and Greg Murray will come in over to talk about the data acquisition software. D2T is a partner company of HBM, and Greg, it's all yours.
Thank you very much, Sujit, for the introduction to the Dyno application. Now we will review the software side of the Dynamometer application. I will introduce to you the Morphee software, which is a data acquisition and automation software from D2T. Morphee has been running for over 20 years. It's been created for engine and powertrain application mainly. It's in place, it's running about 4,000 TestCell all over the world, and it's a very open platform, as I will show you in the next few slides. Morphee is reliable, it's powerful, and it's an open platform, which comes with a full package of applications for your engine testing, your engine calibration, or your powertrain testing. But it's also an open platform, so you can modify it for your needs, and you can also use it for component testing, for example. Now we will go through a typical Dyno application. In this case, it's engine Dyno application, as you can see. You have the engine, which is connected through the shaft and torque meter to the dynamometer, and you have the automation system, which is Morphee in this case. So Morphee can mainly do two things in the engine dynamometer application. Morphee can read information first, so that's why it's the data acquisition software, through the EtherCAT bus in real time up to 10 kHz. We're going to be able to read temperature, pressure, different analog signals, but also control analog signals and control digital outputs. Also, Morphee will be capable of reading values coming from smart equipment such as emission bench, smoke meter, or combustion analysis systems. Of course, same as the smart equipment, Morphee can connect real-time to your PLC for your safety, for example, or for everything that's related to the building application. On the other side, Morphee can also control the dyno, of course. So Morphee is going to control the dyno, it's going to control the speed and torque that you want the engine to perform. So through the Morphee system and the control unit, we're going to be able to send speed, torque, and also throttle values. Once we decide which of those three we're going to control, the power cabinet is going to turn the speed and torque signals into current to apply to the dynamometer in order to produce torque from the engine. If the engine is producing torque, then the dynamometer will get the current from the engine, and the power cabinet will be smart enough to push that current to the grid. Of course, once Morphee has recorded all the data from the data acquisition and from the control unit, Morphee will record everything under one file. So everything will be recorded and synchronized under one time base, and the results are going to be saved locally on your Morphee computer, but also, of course, they can be shared on a server. This way, when the test is completed, the engineers have access to their data, and they know what to perform for the next step, or they know what to change, what to modify in order to perform their next test. Now we will see a few benefits of Morphee used in a dyno application. We've seen that Morphee is a real-time system that can run up to 10 kHz. It's a centralized system, which means it's running on one computer. It's only one PC, it's Windows-based, and we guarantee the real-time on a Windows platform using RTX software. So we have a software kernel, real-time kernel, which allows us to make sure we deliver a real 10 kHz real-time. It's also versatile because we will see in the next few slides that using the Morphee system, you can control your engine testing, but also your powertrain testing and your component testing. In order to do that, it's an open platform, so you can modify your test description, and also you can modify the hardware you're using. This way, if you are using or not an emission bench, for example, in your test, in your TestCell, you can use the same test description using Morphee, with or without the hardware in the TestCell. Since it's PC-based, of course, we are taking advantage of the multi-core processor technology. That means we can increase the power of the automation system, and it's also why we call that an open platform, because if you want to expand your testing capabilities, you can put new boards in your computer, and that will give you more capabilities in terms of data acquisition, but also smart devices that you can plug to your automation software. Morphee is also capable of doing simulation. It's very important in today's testing because you don't always get the chance to have the prototype available to do testing with your current hardware. So in order to do that, you can create a model of your prototype, of your new hardware, and you can link this prototype or this simulated prototype to your real hardware using simulation. In order to do that, you can use simulation directly on the Morphee computer, and you can use a compiled model, which means you don't need to have all the licenses for your simulation tools on the Morphee computer. So you can use your models real-time without the cost of all the licenses. I mentioned earlier that Morphee is real-time. It's what we call hard real-time because with the internal clock, we guarantee that there will be no drift and the data will always be synchronized. So there will be no missing information or no repeated information. There will be no duplicate. That's what we call the hard real-time. Of course, Morphee is also capable of working with the Test sensor. It's a unique feature in Morphee for an automation software. We have a fully integrated solution for the test technology where we actually have a test editor in order to take full advantage of the test technology. In order to do an open platform, to be an open platform, Morphee is delivered with a real-time software, but also with the Morphee editor, which will allow you to modify your test description and to create your own screens, your own subroutines, and manage your different data acquisition channels. So the Morphee editor comes with an Outlook look because it's a .NET application. So you can see from the left side here, I have my list of test descriptions. Here it's a very short list. For the demo, you can have as many test descriptions as you want. And for example, if I select the full load test, the full load test description, I will see more information about what is actually in my full load description in the work area in the center. You see the test description is made of methods, so those are the subroutines internal in Morphee. They are made of screens. Of course, you can manage your own screens. Morphee comes with different packages for engine testing, powertrain testing, diesel, gas, two-stroke, four-stroke applications, but you can modify your own screens so the operator can have the look and feel they want. And finally, we have quantities to describe a test description. The quantities are all the variables which are linked to physical channels or that are internal variables. Here, to give you an example, using the components technology in Morphee, that's only the 12 channels that we need in order to perform a full load test. So that means we have all the channels, all the inputs from the data acquisition that are defined in the data acquisition in the engine control components. But for the test description, we only have a handful of channels, which makes things very easy and which allows you to share the test description between the different test cells if you have more than one test cell in your test center. The test description is also very simple because, as you can see here, we use a graphical interface. So it's a proprietary language that is defined inside Morphee, which again is installed and commissioned in order to perform your testing, but it's also open, so you can modify it and you can change the way the tests are defined, or you can tweak the test based on the engineer's requirements. The Morphee configuration, we will see now how the link is made between Morphee and the hardware in order to bring the values from the QuantumX hardware inside the Morphee software. Here, that's the example without the test technology. So once you create a Morphee channel, which is here a voltage input, for example, The only thing you have to do is to select through your drop-down list which physical channel you want to link to that software channel. Here, for example, I'm going to call my voltage input the channel that is on the slave 3 of the HBM and which is on the channel 29. Once this channel is selected, of course, it won't be able to be changed and it will be set in the Morphee software. On the other hand, using the tags now, you see, in order to create an engine temperature channel, for example here, we will only select the physical channel auto, which means as soon as we have a test sensor that will be connected to the Morphee system, called ing_temp, Morphee will recognize that channel and will be able to record that value and also to use it in the calculations. We will go through now a quick demonstration of the test capabilities. You see here at the top, that's what a Morphee screen would look like. And at the bottom, that's a very simple test application where we have the orange cable, which is the EtherCAT cable, which allows us to read the values from the QuantumX hardware up to 10 kHz. And here you can see this orange sub-D, which is the TED sensor. So here I have my TED sensor called engine temp, which is reading a value of 23.59. If I unplug that TED sensor, I just don't get the value anymore. I don't have to restart Morphee or to restart the hardware. Everything is running, I just don't get this value anymore. Once I reconnect this sensor to a different spot, you see now in a different plug, Morphee knows how to recognize this engine temp channel, and Morphee can read now the 23.6719 temperature. So automatically, without restarting the software or without restarting the hardware, you can plug and unplug your sensors. This is a screenshot of an example of a Morphee demonstration. So that's what the operator would see when Morphee is running at 10 kHz. Here in this example, it's very simple. You can see on the screen, on the bar graph in the middle, the red line is the speed of the engine, so it's the engine RPM. We start the engine, and then we set the engine speed to 1500 to set the engine to the starting condition for our test. You can see the green line, which is the torque, so that's the result of the speed we're applying, and the orange here, which is the throttle, 200%. Of course, for those screens, we said you can modify them. You see you have different tools which are you can modify fully those different tools, such as the bar graph, the simple display, you have LEDs, push buttons, full range of tools that are available for you to design your own screen. Now, if we look at the detail of an example of a full load application, the full load test, just the same as earlier, we can see we started the engine using Morphee, and then we set the throttle to 100%. And then we're going to go through the different steps, different RPM. This way we'll be able to build the power curve for that particular engine. You see now the green line, which is the torque, which is the result of what we're applying to the dyno. The torque is changing based on the engine specifications and based on the calibration of the engine. You can see here on the left-hand side that Morphee is controlling the dyno, of course, and Morphee is setting the dyno to speed throttle mode. That's why we are able in the Morphee software to set the throttle, opening, and the RPM of the engine. A more detailed screenshot of the different hardware that is linked to Morphee. We said earlier that Morphee is the center of the dyno application. So we control the dyno, but also we get the values from the data acquisition. So we get all the temperatures and pressures from the engine and from the surroundings of the engine. But also we get all the smart measurements. We get the consumption from the consumption system. We get the smoke from the smoke meter, opacity meter, and also all the conditioning that we want to control so the engine performs in a specific way and in a controlled environment. So we have the air conditioning, the exhaust, water, oil, and fuel conditioning. Everything is linked in Morphee and synchronized. You can see here at the bottom there's the A01, which is the one single file that is created with all this information, which is available for the engineer at the end of the test. A quick summary, I will switch back to Sajid for the final words.
Thank you, Greg, for the nice description of the D2T Morphee software on the AC Dyno testing. To summarize our presentation today, dyno testing faces many challenges in today's environment. The time to market, the accuracy and repeatability are its core. And using HBM's QuantumX data acquisition hardware and sensors, as well as D2T Morphee software, one can easily address these challenges that's available to your market right now. QuantumX DAQ, which is TEDS and EtherCAT technology, makes it scalable and easy to integrate and deploy that enhances confidence in your acquired data. And on the other hand, D2T's Morphee software can bring you an open platform for data acquisition integration and fast 10 kilohertz EtherCAT rates. Please contact www.hbm.com for more information, and thank you for your attendance and participation in today's seminar.
Okay, thank you, gentlemen. So we have some time for a couple of questions here. So we'll just jump right into the Q&A portion of the webinar. I'm going to unmute the presenters' lines here so they could answer the following questions. The first question that's come in is, how many channels or variables can be integrated in the system?
Sajid, if
Yes.
you let me answer that.
Go ahead.
The system is fully open, and there's no limitation to the number of channels you can link to the automation software. So you can add more QuantumX modules, you can add more boards in the Morphee computer if you want to perform a test with more channels, but there's no physical limitation or hard limitation in the software.
Okay, great. We have another question here. I'm running 100 hertz data acquisition today. Why would I need to run 10 kilohertz system?
It's a very good question. Of course, the temperatures are not changing very fast. So that's why people tend to say, I don't need to use a very fast data acquisition system. The only thing is today we can communicate directly with the ECU. So that means the ECU is usually running at up to 10 kilohertz, maybe more. So we need to communicate with that ECU very fast. Also, we have other applications such as the simulation or the models which are running at a very high frequency. So in order for those models to perform fine, we want to run at a very high frequency, and that's why 100 Hertz is not enough anymore in today's testing environment.
Okay, great. Thank you, Gregory. So we're just about out of time, so we shall wrap up the webinar, and wanted to thank everyone who attended today's webinar, and thank our presenters Sujit Basu and Gregory Marouz. I shall send the PDF slides of this presentation to those who registered within the hour, and the recording to this webinar will be posted on our website within the next couple of days. So thank you again, everyone, and have a great rest of the day.